All right. Well, welcome everyone. We've had a bit of a rearrangement to the schedule. There is a lot of stuff to cover on generative models, and we're still working on curriculum development for the diffusion lecture and the diffusion model lab. So for that reason, we've done a little bit of rearrangement with our schedule, and we are going straight into deep reinforcement learning today. And then we'll be doing the deep reinforcement lab next week. So yeah, this is a fun unit. So yeah, I got a little XKCD comic on the theme of reinforcement learning. Reinforcement learning is generally, well, it has lots of applications, but some of the main applications are in robotics and yeah, so that's kind of where this XKCD ties in. So as far as business, yeah, I've given feedback on all of your final projects. That feedback is on Learning Suite. If you don't have any feedback, that means that I had no suggestions to improve your project. So you're good to go ahead as is. You're still good to go ahead if I gave feedback, but just take that feedback into consideration. And we have readings as usual. Yeah, hang in there. We're on the third to last lab, so you are 70% of the way there after this Saturday. So, and actually, these do not apply because we have not hit that lecture yet. So, yeah, today we're going to start right into deep reinforcement learning. So this is a quick video from a multi-agent environment where agents were trained to play hide and seek. This is out of OpenAI.
Today, yes. And also, the new easy. They've already learned to chip away. In millions. Learn to use rudimentary. Seekers are brief period. Even so, learn to collect, accomplishing. Not the only one. Generation. Seekers learn over in rap. Millions of new pressure. We've also into a more open, inside this world. Learn to construct shelter. Multiple. To prevent seekers from using them. Move them to the unlocked. Originally believed to be the more training. Seekers. New agent. Reinforce. Move on. The agent. Again, gather. However, this world. Simple. Recently, multi-agent. We hope that much truly one day emerge
It is. Yeah, they really put a positive spin on things, don't they? Yeah, it's kind of, I think, Sophie, that's a great comment, because yeah, it's kind of fun and entertaining to see these cute little figures learn these emergent behaviors, but once you start strapping a gun to them, it starts becoming a lot less funny. And take away and replace the happy xylophone music with some more ominous music. So yeah, I think just from watching that video, what are some thoughts or impressions that you had of, obviously you don't know anything about the specific algorithms that are used, but yeah, what thoughts did you have on the video? Jacob, did you have something?
I thought it was really interesting just seeing the progression of the AI without any supervision. It made all these new strategies and felt like, I don't know, if you've ever watched like StarCraft, it's like the same kind of a thing. Well, a new strategy gets developed and then someone counters it, but it was a computer doing that, not a person.
Totally, yeah. Emergent strategies from simple games and those strategies building on each other. Yeah, Michael.
I just thought it was like awesome that they were able to learn teamwork, because those AIs were able to like work together better than some of the group projects that I've had at college.
Yeah, interesting. Yeah, agents learning to cooperate and perhaps even specialize in different tasks. Yeah, totally. Any other thoughts?
I was curious.
I'm gonna. Well, so we want it for the recording.
Oh, for the recording. Because the kind of like he was saying, the strategies would play off each other, and they would counter and then learn a new one and then counter. I'd be curious to see if you played the first version against the last version, would it still counter the first strategy, or would it have unlearned the first strategy to learn the last strategy?
Yeah, that's a very interesting question. Whether these strategies build on each other, or whether there's some issue of forgetting. And spoiler alert, it's very easy for reinforcement learning agents to adapt to the current state of its training and forget previous things. So that's definitely a real problem. That's a great observation. Any other thoughts?
I just think it's cool how well it sort of matches how real evolution happens with like bacteria, how they'll learn incrementally, but then occasionally just have a huge jump as if they're trying a new strategy. It's neat how it mimics that so well.
Yeah, that's I think another really interesting observation where it seems like there are these jumps, whereas in a lot of the deep learning problems that we've seen so far, we have a pretty continuous reward signal, which makes it really easy to optimize by gradient descent. But when those rewards are more sparse and you have to like kind of win the jackpot, how do you deal with those more sparse rewards and those jumps in performance? Any other thoughts? Yeah, a couple of my thoughts on it. I think there are a couple of powerful principles at play in this demo. One is the idea of using an environment with rules baked into it to try to learn very complex behaviors. In reinforcement learning, you don't have, it's different from supervised learning where you have pairs of inputs and outputs. Instead, you basically have unlimited data in the form of interacting with this environment. You can imagine, like, what if we allowed these agents to communicate through a keyboard? Like, would they learn some sort of code language that would allow them to communicate in a way that helps them improve? Looking at emergent language from reinforcement learning scenarios, or even if we constrain them to speak in English with each other, would we be able to, number one, would they learn faster if we equip them with language? Number two, would equipping them with language make their strategies more interpretable? So a lot of interesting questions there. My other takeaway from that is the fact that sometimes by setting up the environment in a certain way, the creators had an intended strategy that they wanted the agents to discover. But then they discovered like other strategies that the environment allowed, but which were not intended by the creators. And I think, to me, that is honestly a pretty big warning sign and red flag, because there's a general principle in AI that whatever is not constrained, the agent will take advantage of. And so you can imagine training, you want to train a reinforcement learning agent to do good in the world by, let's say, preserving some endangered species. In the process of doing so, if you don't set up your constraints well enough, it might end up wiping out all of humanity or something like that, you know. So, and I think, you know, these are I'm not saying that these are necessarily my concerns with AI, but they're concerns that people talk about a lot with regards to reinforcement learning. Yeah, how do you constrain the agents to not do things that you don't want them to on their way to learning these strategies in these open-ended environments? So yeah, any more comments on that before we move on? Yeah, Jaden.
I saw a really fun video about this exact same project where instead of just surfing the blocks, it also had the agents going into like taking advantage of the physics engine in another way that would just throw them over the walls by like a huge amount, and they would just fly through the air and then just nuke the other party.
Yeah, so other interesting examples of taking advantage of the open-ended environment, do things outside the intended learned strategies. And obviously, like it doesn't do us much good to have agents learn strategies that we already know in most scenarios. Like the purpose of artificial intelligence is hopefully at some point to supersede human intelligence. So yeah, how do you allow it to learn new strategies without those strategies becoming dangerous? These are questions to ask. Yeah.
Could you utilize this to find those weaknesses, to find the constraints that can be broken so that you can fix them, like put them into a system to find security, stuff like that?
Yeah, totally. That's definitely a possibility. Mm-hmm.
I have a question for like the class in general. So are the readings going to be updated for next class?
Yes. Good question. I have not updated the readings yet, but the answer is I'm not sure. I haven't actually taken a look at the readings for next week, but I will take a look at those and update you on the Slack. Thanks. Okay, so we are going to move on to how these reinforcement learning algorithms actually work. Oops. Okay, so yeah, the reinforcement learning occurs at the intersection of many different fields, and it doesn't. And reinforcement learning is actually not constrained to deep reinforcement learning. Reinforcement learning as a field of study has existed for at least 70 years in the form of dynamic programming and Bellman equations and things like that. It's only in the last 10 or 15 years that people have started using neural networks for reinforcement learning. So that's something to keep in mind. Yeah, so in reinforcement learning, we have an environment, and that environment provides us with four things. It provides us a set of states, S, a set of actions, A, which can be taken from those states. It provides us a reward function, which takes as input a state, an action, and a new state, and provides a reward in the form of some number, as well as a transitions function that tells us, given a state and an action, what the next state will be. And generally in reinforcement learning, we are going to train some sort of thing that we will call an agent. And that agent can be value-based, policy-based, or model-based. And we will explain what each of those mean. So yeah, this is a very common type of diagram you will see in reinforcement learning, where you have an environment and you have an agent that interacts with the environment via actions, and then the environment returns a reward and a state. So there are lots of first of all, there's a huge vocabulary to learn when it comes to reinforcement learning. There is model-based reinforcement learning versus model-free reinforcement learning. There is on-policy versus off-policy reinforcement learning. There is online versus offline reinforcement learning. Those are different from on-policy and off-policy. And a variety of algorithms. So don't feel too overwhelmed right at the beginning. But yeah, we're gonna break these down. So model-based RL is reinforcement learning where we can observe or estimate the environment. We know basically what will happen if we take a certain action. An example of that would be like the game of chess, where we know, given a state and an action, what the next state will be. Model-free RL is where we don't know what will happen in an environment based on an action. And so instead, we have to basically make our best guess at an action based on some reward signal that we're getting from the environment. And within model-free reinforcement learning, there's value-based learning, also known as Q learning, and policy-based learning. An example of a policy-based learning algorithm is called policy gradient. Yeah, and then deep RL is using deep learning to learn as using gradient-based methods for gradient-based versions of Q learning and policy gradient, where our agent is a parameterized neural network. So today we're going to be talking about value-based learning, and specifically the Q learning algorithm. So first of all, we're going to start by talking about Q learning without a neural network. Our agent is going to be a table of values. And yeah, let's start with this equation. So the way that Q learning works is we are going to learn this Q function, which is a function of a state and an action. And we want to learn basically the value of all actions out of a given state. And then if we want to maximize our reward in the environment, we will just take the action that has the highest value in a given state. Any questions on how we would use a known Q function to take actions? Yeah. In this case, it's a discrete space. Yeah, we'll look at continuous action spaces later, but in this case, we're looking at a discrete space. Yeah, Drake. Yep. Yeah, and great question. So the Q function returns the expected discounted sum of rewards. So very close to the expected reward, except we're going to have a discount term for future rewards, so that it's motivated to take actions that will give it reward in the near term more than in the long term. Yeah. Oh, good question. Pi. So pi is our policy. It's our policy function. So we're going to say, given a trained Q function, our policy will be to take the maximum value action. Sense? Okay. Yeah, so a policy takes as input a state and returns an action. Okay, so this is an example Q table, and I believe we have oh no, we don't even know what our environment looks like yet. But basically, it looks like our environment has 8 different states, and we have 4 different actions corresponding to these different arrows. And from each of those states, each arrow has a different value. So this is an example of a trained Q function. So yeah, and so as an example, if we were to take this trained Q function and we were starting in state 4, where would our policy tell us to go? Up, right? Okay, and let's say that S3 is above S4. What would our policy tell us to do? Go to the right, because that's the maximum value, etc. Yeah, I think you got the idea for how we use our learned Q function. But how do we get our Q function? And it gets a bit complicated. So our Q function, we are going to define to be, it will take as input a state at time t and an action at time t. And we want it to return the reward for that state for the current time step, plus some weighting function gamma times the reward for the next time step, plus gamma squared times the reward for the next time step, plus gamma cubed times the reward for the next time step, et cetera, et cetera, et cetera. And so gamma is our discount factor, where gamma is going to be between 0 and 1. And so as we basically accumulate terms farther into the future, gamma will make that term smaller and smaller and smaller. Yeah, Jayden. Good question. It depends. Yeah. So in some cases, we will know what happens in the future. In some cases, we will not. So usually RT is a given value, or RT plus 1 is a given value, and often the remaining rewards will be predicted values. And so I think it'll make more sense when we get into like the particular variations of Q learning. But that's the right question to be asking, like which of these are predicted and which of them are given. So yeah, you can see that we can simplify this first equation by factoring out a gamma term from the last every term except the first, and that gives us RT plus 1 plus gamma times the maximum over all actions at the future time step of the future discounted sum of rewards. And so there's kind of a recursive element of to this equation, because you can see RT plus 2 plus gamma, et cetera, is exactly our original Q function, but with ST plus 1 and AT plus 1. So we can replace everything inside these brackets with Q ST plus 1 and AT plus 1, and that gives us this equation right here, which we will call our Bellman equation. And it's a recursive equation where it says that the value of the current time step is the reward for this time step plus gamma times the value function for the next time step. Any questions on, does that kind of make sense how we can express the value function of our current time step in terms of the value function of future time steps? Okay. And then, yeah, so then once we have this Bellman equation, we can define an update rule. So we now are no longer assuming that Q is true. We don't know Q yet. We're just basically randomly initializing this Q grid of values. And we want to learn the values in this grid. So to do that, this will be our value iteration rule. We are going to say that our updated Q of a state in action is our current Q plus some hyperparameter alpha, some weight, times the difference between our true value, so this R plus gamma max of Q, that will be our target value function, and then minus Q of SA, that will be our current value function. So basically, we're going to sample from the environment and get an actual reward, and then we will approximate our future value and take the difference between the actual reward plus the approximated value and our current approximated value, and that will be our learning signal. Does that seem weird to you guys at all? It probably should. We're using what? Yeah, so this, we probably should put like QT plus 1 on the left-hand side and QT on the right-hand side of the equation, just to make it more clear. But yeah, so that's one thing. So on the left-hand side is our updated Q. The other thing that I'm hoping seems weird to you is the fact that we are using an approximation for our future value as a target for our current value. Any ideas why that might actually work? Yeah, Spencer. Yeah, I think that's a good analogy. So Spencer said, yeah, it's like trying to approximate the speed of your car in the future based on what happened when you pressed the pedal in the past, something like that. Yeah, you have a thought?
Like, what are you learning? You're not learning alpha, are you? Or are you learning the future Q values?
Yeah, great question. So we are not learning alpha. Alpha is a hyperparameter that we select. We are learning Q. Yeah. So I'll tell you kind of basically the whole idea here is that we in our target, even though a lot of our target is approximated by our previous value of Q, we have a tiny bit of signal here that we got from our environment in R. R is true training signal from our environment. So we're basically going to update Q based on an approximation of the value of our future state plus this true signal R. And that little bit of signal R is going to be enough to help us update Q. Yeah, Travis. How do we get our predicted value? So that will just come from looking in our Q table at the future state and actions. Yep. Yeah, and so we could even do an example here. So let's say we're starting at S6, and we want to find the value of S6 with action 1. Well, we are going, and actually, you know, we have a worked example of this on the next slide. So let's move on. So this little graph on the left is going to be our environment, and it tells us how we move from one state to another via different actions. So if we're in state 1 and we take action 2, which state will we move to? S3, correct. and what will be, and then the reward is denoted by the number associated with that line. So S1 plus A2 gives us a reward of 1 and takes us to state 3. What if we take action 1? What will our reward be and what will our state be? If we take action 1, then our reward will be 10 and our new state will be S2. And then if we're in S2, what actions can we take? We can only take one action, A3, which will return us to state 2 and will give us a reward of 1. Same thing with S3, there's only one action, which returns us to S3 and gives us a reward of 10. So let's see if we can figure out what the Q values of S1A1 and S1A2 are. Okay, so Q of S1A1 is going to be the reward associated with A1 plus gamma times the reward associated with the next action and so on. And we have, there's a very particular reason why we've chosen this environment. And it is because once we're in state 2, we have to stay in state 2. And once we are in state 3, we have to stay in state 3. And so because of that, R3 will be equal to R2, and R4 will be equal to R2, et cetera, et cetera, et cetera. Does that make sense? So normally this would say R3, R4, et cetera, but we are replacing those all with R2, which because gamma is between 0 and 1, this becomes a geometric series that converges to this value right here, R2 over 1 minus gamma minus R2. Okay. And so we can plug in our numbers there. R1 is 10. R2 is 1. 1 over gamma is 1 minus 0.9, which is 0.1, and then minus 1, which is R2. So Q of S1A1 is 19, given a gamma of 0.9. This number will change if we change gamma. Okay, any questions on how we got Q of S1A1? Yeah. Great question. Yeah, that is exactly what that gamma represents. So, yeah, well, yeah, kind of. So gamma is a weight on how much we value future rewards. And so if gamma is low, then it means we are incentivized to take like the maximum value actions right now. And if gamma is high, then we are incentivized to take actions that will lead to payoff in the future. So it's kind of related to exploration versus exploitation. Okay, so then let's do Q of S1A2. So we have the exact same formula because R3 will be equal to R2, et cetera, et cetera. So we have the same formula. This time R1 is 1, R2 is 10, and 1 minus gamma is 0.1. So in this case, our value function will be 91, which makes sense because basically the state that we stay in for infinity time gives us better reward if we take A2 compared to taking A1. So we didn't have to use any value iteration here. We chose an environment that let us basically combine all of these terms in a geometric series, which worked out really nicely for getting an exact value function for a given gamma. It doesn't always work out like that. In fact, it basically never works out like that. But in this case, we were able to find a closed form for our value function. If we change gamma, the equation remains the same, but you can see, and this is kind of what you were asking about, what does gamma value? It values the proximity of your reward. So if we now say the future is not important with a gamma value of 0.1, taking action 1 now has a value of 10.11, and taking action 2 has a value of 2.11 because we value this first reward much more highly. Yeah, Max. Great question. So yeah, the question is, if there is not a closed form to Q, do we just approximate it by going out as far as we can? So there are two options that I'm aware of that people use. One is what I showed you on that first slide, where we use the current reward and an approximation for our future reward, and that becomes our target. The other is we do what's called a rollout in the environment, and we just say we interact with the environment until the environment terminates, and then we have an actual reward for that action given that rollout, and that becomes our target. So one Q target comes from a rollout, and the other comes from a single time step plus an approximation. Yeah, Jared. Yeah, that's usually how you'll do it if you don't have an end condition. Okay. So yeah, if we say the important, and then if we have a gamma of 0.5, then turns out that the value of both of these state action pairs are equal. Okay, so this is the formula where we use reward for a single time step plus an approximation of future rewards as our target. So this is the Q-learning algorithm, or this is the value iteration algorithm where we don't have a closed form. So until convergence, we sample a random state, and then for a given period of time, we choose an action out of that state. And that can be by choosing the maximum value action. That can be by sampling an action randomly. So choose there can be multiple options for how you choose your next action. Then you interact with the environment using that action to get a reward in a new state. And then we perform our Q update. Does someone want to, I've explained this equation a couple of times so far today. Does someone else want to try to take a shot at explaining this Q update equation? You're going to have to do this for your lab next week. So if you don't understand it, it was probably good to try to take a shot at it and see if you can get to the point where you understand it today. Yeah. Just this step where we update Q. I'm going to give you the microphone, so yeah.
Okay. Basically, we update Q based on the current value of Q, like where we're at right now, what state we're in, and we can get the actual reward, like the real reward that we by interacting with our environment. And then we look into the future, however many, I think probably just the next time step, and we estimate what our reward's going to be based on taking the action that we chose earlier, and what state we're going to end up in. And then we and we take them. Yeah, so we add those two together, and then we subtract the current reward from where we're at right now. I don't know. That was really jumpy.
Yeah, that's pretty good. Yeah. So just to reiterate that one more time, we're updating our value function Q, and our target for the value of the current state in action will be the reward of that action plus the Q function of the state that action will take us to. So the given reward of our action plus the value of the new state given by our action will give us our target. And then we'll take the difference between that and our current Q function value. Any questions on that? Yeah. Good question. Yeah, so usually that's just one time step. But you can think of variants where you, try to like expand inside this equation and look several steps into the future as well. Yeah, Jaden.
So function.
Correct. Yep. Q in this scenario so far is just a set of weights. Yeah. Great question. Yeah. How do you extend this to a continuous case? We will get there by the end of today. But good question. Yeah, Dane. Something like this. All right. Yeah. Let's go through a worked example. Yeah. So here we have a dinosaur in it's not even a maze, it's just a grid, who is trying to reach this palm tree. And so this grid is our environment. The green numbers in parentheses represent the reward for moving into that square. So you get a -1 reward for moving off the grid, a 0 reward for moving on the grid, and a reward of 9 for getting to the goal. And on the left side of this slide here, we are just defining our state space, our action space, our rewards, our reward for state action pairs, and our transition function for state action pairs. So these things on the left side of the page define our environment. Any questions on that? Yeah, Jared. The reward that we have set, the reward we have set is not our Q table. So if you remember, our Q table is trying to approximate the maximum discounted sum of rewards for the entire, until the environment is over. Whereas these are just the rewards for a single action. Yeah, good question. Yeah. Exactly. Yeah. So totally. Yeah. So the whole. Yeah. We will update our Q table based on the rewards that we're getting. Yeah. Yeah. No. So the question is whether the Q table changes when we move to a new state. So if you remember, the rows of the Q table were different states and the columns were actions. So when we move to a new state, we're basically just moving to a different row of the table. Okay, let's work this example. This is just the Python version of that environment. Okay, so we are going to follow our Q learning algorithm to update our Q table. And so right now our Q table is initialized with all zeros. So our dyno is going to start in state 6, I believe. 1, 2, 3, 4, 5, 6. And we are going to, we sampled a random state, and now we are choosing an action, and we're choosing the go left action. And we get a reward and a new state. So the new state is state 5, and the reward is 0. Any questions on that so far? Yeah, Chase? Well, so yeah, we haven't gone to the Q update yet. So now we are going to perform our Q update. So let's plug it. Let's and you didn't see that. Let's see if we can figure out what our Q update should be. So what is Q of SA? I guess first of all, what is S and what is A? Actually, no. S is 6, and A is left. Okay. So Q of SA is 0. And alpha is just going to be some hyperparameter. What will R be? 0, because moving to a new square on the grid, it has a reward of 0. And then gamma is a hyperparameter. And then the maximum, we are going to take the maximum over all actions in the new state, the maximum Q value of all actions in the new state. So what is S prime? 5. And what is the maximum over A prime? What is the maximum over actions of Q of S prime, Q of S5? It's 0. Yeah, so it will be gamma times 0. So R is 0 plus gamma times 0 minus 0 is 0 added to 0. So there is no change to our Q value. So that was not a very helpful action for learning, but it was helpful for our learning, because I think we're starting to understand this Q update algorithm. Okay. So yeah, the update is 0 and no change. Let's do something more interesting. We're going to sample a new random state. This state is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we are going to choose an action. Oh, look, we chose the action that took us to the final reward. So that's great. So our action is down. So then what would R and S prime be for that action? R would be, I actually don't remember. I think it was 9, yeah. And then S prime would be 15. Yep. So then R would be in our Q update, Q of SA is what? 0. R is 9. Maximum over A prime of that future state. So actually, this is going to be an end state. And so we will say that this equals 0. And then minus Q of SA is 0. So our update will be 0 plus alpha times 9 plus 0 minus 0. And it looks like alpha is going to be 0.9. And so our new value is 0.9 times 9, which is 8.1. And that will be our new value for state 11. Or for state 11 and action down. Okay, any questions on that? Jacob? Similar, so Markov chain Monte Carlo is a sampling algorithm. So they're similar in that we are sampling random state. Yeah, Markov chain Monte Carlo. Yeah, you're transitioning between states and getting different probabilities for those states, which you could kind of think of as rewards. Yeah, I think that's a reasonable analogy. Yeah, Chase. Yeah, so the question is whether you could do that like this deterministically instead of randomly, and the answer is probably yes. I'm not sure about the convergence properties of like choosing deterministically versus randomly. There are a lot of theoretical results in reinforcement learning for for these algorithms, and so I want to be careful to not say that you can do things deterministically, because that might mess up your theoretic guarantees. But that in this case, that could probably work. And that's where we will end for today.